Motor control centers, commonly referred to as MCC, house various electrical components, including breakers, contactors, and other control devices, within individual compartments or buckets. A key consideration when working with MCC is the proper sizing of conductors within these buckets, specifically determining whether the wiring from the breaker to the contactor or contactors should be considered as installed in a raceway or in free air for ampacity adjustment purposes. Article 384 of the National Electrical Code, or NEC, addresses switchboards and panel boards. However, it does not provide specific guidance on the application of ampacity adjustment factors for conductors located within an MCC bucket. This lack of explicit direction necessitates a more nuanced approach to ensure code compliance and safe operation. The primary challenge lies in characterizing the environment surrounding the conductors within the MCC bucket. If the conductors are installed in a conduit, tubing, or another type of enclosed raceway within the bucket, the ampacity must be adjusted based on the number of current carrying conductors in the raceway and the ambient temperature, as per NEC tables 310.15b3 and 310.16. This is because the heat generated by the conductors is trapped within the raceway, leading to a higher operating temperature and a reduction in the conductor's ability to carry current safely. On the other hand, if the conductors are considered to be installed in free air, a higher ampacity may be permitted, as the heat generated by the conductors can dissipate more readily into the surrounding environment. The NEC defines free air as conditions where the conductors are not enclosed in a raceway or cable and have sufficient space around them to allow for adequate ventilation. Several factors contribute to the determination of whether the wiring within an MCC bucket is considered to be in free air. Firstly, the physical construction of the MCC bucket plays a significant role. While the bucket itself is enclosed with a cover to protect the components and personnel, the presence of ventilation openings is crucial. Many MCC buckets are designed with ventilation slots or louvers to allow for the circulation of air, which helps to remove heat generated by the electrical components. If the ventilation openings are sufficient to provide adequate airflow around the conductors, it may be reasonable to consider the wiring as being in free air. Secondly, the arrangement of the conductors within the bucket is also important. If the conductors are tightly bundled together or are in close proximity to other heat-generating components, the ability of the conductors to dissipate heat is reduced. In such cases, it may be more appropriate to apply ampacity adjustment factors as if the conductors were installed in a raceway. Thirdly, the ambient temperature within the MCC room or area must be taken into account. If the ambient temperature is high, the conductors will operate at a higher temperature, which will reduce their ampacity. In these situations, it may be necessary to apply additional ampacity adjustment factors, regardless of whether the wiring is considered to be in free air or in a raceway. Given the ambiguity in the NEC and the varying designs of MCC, the most prudent approach is to consult with the equipment manufacturer. The manufacturer will have specific information about the design of the MCC bucket, including the ventilation characteristics and the recommended wiring practices. They can provide guidance on the appropriate ampacity adjustment factors to use for the wiring within the bucket. This approach ensures compliance with the NEC and safe operation of the equipment. In the absence of specific guidance from the equipment manufacturer, it may be necessary to perform a detailed engineering analysis to determine the appropriate ampacity adjustment factors. This analysis should take into account the factors mentioned earlier, such as the physical construction of the MCC bucket, the arrangement of the conductors, and the ambient temperature. It may also be necessary to perform thermal modeling to determine the temperature rise of the conductors under different loading conditions. Several sections of the NEC are relevant to the determination of ampacity for conductors in MCC buckets. Firstly, Article 310.15 provides general requirements for ampacity of conductors. This article includes tables that list the allowable ampacities of conductors based on their size, insulation type, and operating temperature. Secondly, Article 310.15b3 provides ampacity adjustment factors for more than 3 current carrying conductors in a raceway or cable. These adjustment factors reduce the ampacity of the conductors to account for the heat generated by multiple conductors in close proximity. Thirdly, Article 310.15c provides ampacity correction factors for ambient temperatures other than 30 degrees Celsius or 86 degrees Fahrenheit. These correction factors adjust the ampacity of the conductors to account for the effect of ambient temperature on their operating temperature. Finally, Article 110.14c addresses conductor termination temperature. This section requires that conductors be terminated in a manner that is consistent with their temperature rating. For example, if a conductor is rated for 75 degrees Celsius, it must be terminated in a device that is also rated for 75 degrees Celsius or higher. To summarize, determining the correct ampacity for conductors in an MCC bucket involves a careful consideration of several factors. Firstly, consult with the equipment manufacturer to obtain specific guidance on the appropriate ampacity adjustment factors. Secondly, evaluate the physical construction of the MCC bucket to determine whether the ventilation is adequate to consider the wiring as being in free air. Thirdly, consider the arrangement of the conductors within the bucket and the ambient temperature in the MCC room or area. Finally, apply the appropriate ampacity adjustment and correction factors from the NEC to ensure that the conductors are properly sized for the application. It's important to note that the NEC is a minimum standard, and in some cases, it may be necessary to exceed the requirements of the code to ensure safe and reliable operation. For example, if the MCC is located in a harsh environment with high ambient temperatures, it may be prudent to use conductors with a higher temperature rating or to provide additional ventilation to the MCC bucket. In addition to the NEC, other industry standards and guidelines may also be relevant to the design and installation of MCC. For example, the National Electrical Manufacturers Association, or NEMA, publishes standards for MCC that provide guidance on various aspects of their design, construction, and testing. These standards can be a valuable resource for engineers and technicians who are involved in the design and installation of MCC. Furthermore, it is essential to follow good engineering practices when working with MCC. This includes performing thorough calculations to determine the appropriate conductor sizes, selecting components that are rated for the application, and ensuring that the MCC is properly grounded and protected against overcurrents. Proper installation and maintenance are also crucial for ensuring the safe and reliable operation of MCC. This includes following the manufacturer's instructions for installation, performing regular inspections to identify potential problems, and implementing a preventative maintenance program to address any issues before they become major problems. In conclusion, determining whether the wires in an MCC bucket are considered in a raceway or in free air for ampacity purposes requires a comprehensive understanding of the NEC industry standards and good engineering practices. Consulting with the equipment manufacturer is crucial, and a thorough analysis of the specific installation conditions is necessary to ensure that the conductors are properly sized and protected. The goal is to achieve compliance with the NEC and to ensure the safe, reliable, and efficient operation of the MCC. Keep in mind that electrical codes and standards are subject to change, and it is essential to stay up to date on the latest requirements. Consulting with a qualified electrical engineer or inspector can provide valuable assistance in navigating the complexities of electrical codes and ensuring that electrical installations are safe and compliant. Always prioritize safety when working with electrical equipment. Follow proper lockout/tag-out procedures to energize circuits before working on them. Use appropriate personal protective equipment, and be aware of the potential hazards associated with electricity. By following these guidelines, you can help to ensure the safe and reliable operation of MCC and other electrical equipment. Remember that proper conductor sizing is critical for preventing overheating, insulation breakdown, and potential fire hazards. Choosing the correct conductor size based on the application, installation conditions, and applicable codes and standards is a fundamental aspect of electrical safety. By taking the time to carefully consider all of these factors, you can contribute to a safer and more efficient electrical system. This discussion emphasizes the importance of consulting with the equipment manufacturer and performing a thorough analysis of the specific installation conditions when determining the ampacity of conductors in MCC buckets. While the NEC provides general guidance on ampacity calculations, the unique characteristics of MCC require a more nuanced approach. By following the recommendations outlined above, you can ensure that the conductors are properly sized and protected, contributing to a safer and more reliable electrical system. One additional factor to consider is the potential for harmonic currents in the electrical system. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as variable frequency drives, or VFDs, and other nonlinear loads. These harmonic currents can increase the heating of conductors and other electrical equipment, which can reduce their ampacity. If the electrical system is known to have significant harmonic currents, it may be necessary to apply additional ampacity adjustment factors to account for the increased heating. These adjustment factors are typically provided in the NEC or other industry standards. It is important to consult with a qualified electrical engineer to determine the appropriate adjustment factors to use in these situations. Another important consideration is the coordination of overcurrent protection devices. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. It is essential to coordinate the overcurrent protection devices in an MCC to ensure that they will trip in the event of a fault, protecting the conductors and other equipment from damage. Coordination studies are typically performed by qualified electrical engineers to determine the appropriate settings for the overcurrent protection devices. These studies take into account the ampacity of the conductors, the interrupting rating of the overcurrent protection devices, and the characteristics of the electrical loads. In addition to the above considerations, it is also important to ensure that the MCC is properly grounded. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to protect personnel and equipment from electrical shock and damage. The NEC provides detailed requirements for grounding electrical systems, and it is essential to follow these requirements when installing and maintaining MCC. Proper grounding also helps to reduce the risk of electrical noise and interference, which can disrupt the operation of sensitive electronic equipment. Grounding should be verified through testing. Regular testing and maintenance are also essential for ensuring the continued safe and reliable operation of MCC. Testing should include visual inspections, insulation resistance testing, and other tests to identify potential problems. Maintenance should include cleaning, lubrication, and replacement of worn or damaged components. A well-designed and implemented maintenance program can help to prevent failures and extend the life of the MCC. Finally, it is important to remember that electrical safety is everyone's responsibility. All personnel who work on or around MCC should be properly trained and qualified. They should be aware of the potential hazards associated with electricity and should follow safe work practices at all times. By working together, we can create a safer and more efficient electrical environment. These additional points highlight the importance of considering harmonic currents, overcurrent protection coordination, grounding, and regular testing and maintenance when working with MCC. These factors can significantly impact the safety, reliability, and performance of the electrical system. By addressing these issues proactively, you can help to prevent problems and ensure the long-term success of your electrical installations.